Okay, so we have two problems to do today. One is from chapter 11, the other one in chapter 12. And there is the one from chapter 11, and I'm going to do it several different ways. Okay, I'm planning to spend about maybe 25 minutes on this, several different ways based on what we did in class yesterday. So one option is to create a block, extract the surfaces, and start from that point on. Okay, let me start that way. I'm going to make the block, extract the faces. So let's go here. I always start with a part file until next week when we do assemblies. Okay, starting Monday. Let me start with a part file, file new. All right. So a block that is 5 by 5 by 10, because the dimensions of that folded sheet metal here was 5 by 5 by kind of 10. Let me kill this one too. All right, so let's go there. On that face, I will sketch a 5 by 10 rectangle. These are inches, so this is going to be 10. That's going to be 5. Exit. And padded by 5 inches. Okay. So now remember, you're in generative shape design. You have to switch to part design. So padded by 5 inches, and there is the block. I'm going to make the holes on the top. So on that face, I will sketch. Fit this thing. Okay, so let's make a hole here. And the radius of the hole, I think, is 1 inch, but position of it, we have to be careful because it's exactly in the middle of that. So this is 1 inch, radius is 1 inch. Actually, I don't know, is the radius 1 inch? Diameter, okay, diameter is 1 inch, so radius is 0.5. And I'm going to position this thing exactly halfway between these two. You can dimension it, or you can say this line control that line, control the center, equidistant. That's saying some dimensioning. And then, of course, the other one I have to dimension from here to that center. I want it to be 2.5. 2.5. Okay, exit. We're going to make a pocket here all the way to the end. It really doesn't matter whether it's to the end or not because we're going to extract the top face anyways. I also need something on this side. So on that face, we'll sketch, fit it. Okay, so let's make a circle, radius 0.5, radius 0.5. Position exactly in the middle. So left line, control right line, control the center, equidistant, and top line, control bottom line, control the center, also equidistant. Okay. No, not here. Yes, equidistant. Exit and pocket all the way to the end. It really doesn't matter how far I go, but let me go to the end, to the last. Okay, fine. Now notice that when I did this, inadvertently, I didn't make the plane I made it so that there is no plane in the middle. Okay? Because I want to cut this. You have to use all planes of symmetry. All planes of symmetry. And there is a plane of symmetry which is cutting it like that, except that when I was making it, I didn't pay attention to it. I'm not going to go back. I'm going to make a plane right now. For example, I'm going to make a plane here, offset from that plane by a distance of half, which is 2.5 inches. 2.5 inches. And then I'm going to use this for cutting purposes later on. So this, let's apply material to this. I think the problem says aluminum. Find this to aluminum. Apply material, aluminum on that part, and we say OK. And let's say extract. You have two choices. You can extract the faces now, later. You can extract the faces and then cut it, or you can cut it and then extract the faces. That's entirely up to you. So let me actually cut it right now. Yeah. So where is the split? I mean, the split is somewhere here. There are no magic ways. Of course, you can customize your screen, your interface, so that those things that you use quite often can be put in some kind of a toolbar and things like that. But like 90% of these things I don't use, but they're still sitting there and clogging the screen. Doesn't matter what side we pick. Okay. Now to extract faces, as soon as you say surface, face, you have to go and go to the generative shape design. So you go to generative shape design, look for the thing that is extract, a box pointing to one of the faces. You can do this, and then you can do the other one, or you can do a multi-selection by going to that bag right there. Let's see now. This is hide, just so that you don't get confused. But that guy is sitting in the background. So when we go to generative shape design, generative structure analysis, immediately that box that's hiding is going to get meshed, and I don't want that. So what you do is you make sure that you delete this, and you delete the 3D property, both. Otherwise, you're going to get a hassle by the software later on, and maybe you can figure it out, maybe you can. That's going to be your problem. Okay, so that's pretty much it. Now we have to do the meshing. Okay, so I'm going to do a step. Now, if I don't join these, if I do not join them, there is going to be a seam there, okay, that you have to handle. And we did it yesterday. We did an analysis connection between them, and we made it fasten. So I don't know. You can join it. You don't have to join it. I'm not going to join it, okay? Because I want to show you what we did last night, yesterday. So I'm going to mesh this. There we are. Incidentally, notice that this says use a finer mesh around the holes. Okay, let me try one of them, because it's the same thing that works here works for the other one. And let me see whether we can do that. Let me double click on this, because I'm not sure whether we can do it here or not. Local. See that? The different ways of doing it, but here there's something that says edge distribution. See that? Edge distribution. Add. And I think you can go and select an edge. Support actually. Oh, there. I selected that edge, and it says how many holes you want on it. This is one way of doing it. Okay, there are other ways. So let's make it. I'm going to make it 10, and then say OK, and then show the mesh. There better be finer mesh in that area, and then it's okay. But this is not the only way. So if you're asked to make finer mesh in some area around on the shell, you can do it any way you want. This is one way. Okay. Good. Now let's go to the other one. Deactivate this. Mesh it again with this guy. I'm not going to make it finer around the hole. We know how to do it. Of course, you can look at the mesh. Both of them are going to get displayed. Okay. deactivate. Let's apply thickness. Now notice that in this particular problem, I'm saying the top one I want 0.05 inches and the side I want 0.02 inches. If you don't join, if you joined it and you put a thickness, it's going to go everywhere. But you know how to fix it, how to go and make a finer, a smaller thickness somewhere else. Local mesh, you know, local 2D properties, something like that. But I didn't join it, so that's fine. Let's go here. Here is the thickness, shell thickness on the top, 0.05. 0.05. On the side, 0.02. Very good. And since we know what the story is, if we do all the stuff and then run it, it's going to bomb out because these things don't talk to each other. Let's create our connection right now. Analysis connection. You can do it between this edge and that edge. That's one way of doing it. Or you can do it between this face and for the second component, that face. Notice that it draws that line. If you did it edge to edge, then it puts a white dot there because you can't draw a red line between 2 points, identical 2 points. So it's really the same thing except that you can't see it because the 2 points are sitting on top of each other when you do it edge to edge. And this, we're going to make it, what kind of connection? Fasten, okay. And you go to right here, connection properties, the third one is fasten, and you can select it from here. Put the fastener there. Okay, I don't know whether there's any logic of putting it there, but the last two problems that we did were at the C. Okay. All right, let's go ahead and clamp this edge. I think it says this edge is clamped. And then we push on the top by a force of 100 pounds. Okay? So let's apply a force on that edge. Now, if things are blocking your view, then you have to zoom in or hide them. I think there is a sketch there. There may be a sketch there. So I'm going to hide this. Too lazy to go. I'm going to hide it. Remove all supports. Just want the edge. How much? Half of what was applied. So it is, I think it says 100, right? So minus 50. Minus 50. Okay. And right. So let's go ahead and run. Of course, it's going to deform. Now, if these guys are bothering you, these are those fasten internal elements. So if they're bothering you, you can click on that, and under selection, say, don't show me all the junk. Just show me this mesh and that mesh. Don't show me all these internal elements that are created, maybe contact, maybe fasten, maybe something else. Don't show it to me. Are we good? 26 points for this problem. You all lose about 8 points. Because symmetry conditions did not put in there. Okay? Alright, so deactivate this. Okay, so let's go ahead and fix the symmetry user defined on this edge and that edge. Not face. Okay. This edge. Yeah. This edge. Do not forget to select this edge also. So easy to miss. This edge. Do not select the circle. The circle is clamped anyways, but the circle is not part of the symmetry. And these things, These things lie in the YZ plane, in my YZ plane, so they don't move in X, and rotations are opposite. Okay? It's going to run. If you don't put that thing, they may look the same. Numbers are not the same. Okay. And then you can look at the, von Mises stress, for example. Let's see now. Material shading. Now, you have enough judgment, engineering judgment, to know where the biggest stresses may be. They can be at the seam, they can be at the holes, okay? And whether it's the top hole or the side hole depends on the thicknesses. Remember, the top is very thick, double the thickness of the side one. So it moves kind of as a rigid body with respect to the other fellow. So there is a stress distribution, but it's so thick that this flimsy vertical plate is going to mask the other one. Any questions? Okay. So let me kill this. I want to say something, but I can't remember. Okay, we're going to do it differently. Now, from this point on, I'm not going to worry about dimensions. Okay, I will just go make it. Just go make it. So I'm going to create an extruded L, so that the sides talk to each other and measure. Okay, so let's start with the part file. And you have to be in generative shape design because you're creating a surface. So on that vertical plane, for example, I like to do it on this one. I like it better. So make an L like this. Exit. Extrude it. Let's make it a little bit bigger. Okay, so this is half of that surface, half of that top surface. You can make the whole thing, it doesn't matter. Now, I want to drill a hole up there. I want to make a hole up there. So this is the way it works in surfaces. One way that it works in surfaces. On that top face, I will sketch. Where is this guy? Okay. So the hole, I want to make it down here. Okay. So I'm going to make a circle. So a circle, somewhere there. But I want this center to be on that line. We know how to do that. So this point control that line. Line, coincidence, or dimension and dimension 0, etc. Exit. There is no pocket. There is no pocket. Pocket is only for solid objects. There is no pocket. But there is a split. A split is the saw. And you have used this thing before. I think you have used this before. Click on the saw. Just be careful. This was selected. You see that? This was selected. I didn't want to select this. I wanted to select this guy. Because now if I do something, it's going to go nuts. So cancel that. Unselect that. Click on the split. And read it carefully. Element to cut. Did I select it? No. I want to get rid of this. There is no remove thing. So cancel it. Bite the bullet. I screwed up. Okay. Read it carefully. Element to cut is that surface. Cutting element is that circle. And it says which side of it do you want? Do you want to take the inside or do you want to take the outside? Obviously the inside. There we are. We do the same thing on the side. So on this side, sketch, fit. Where is it now? Yeah, okay, fit. Okay, so normal view, draw a circle like that, exit, and oops, that's on the wrong side. That's on the wrong side. No problem. Let's go back in there. Fit. Now notice that you can move this because there is an order, there is a constraint there. You have to delete the constraint, then you can move it. Yeah. So let me do this. You can completely delete this. That's one way. But let me show you something. Every time there is a constraint in your sketch, that stuff is put in your sketch somewhere. See that constraint? See this? This is that guy, that hole that you see there. You know, you just delete it. Delete it. Now you can move. Now you can move the guy. So I'm going to move this. Now that, control this, and then make it coincident. Okay, exit, exit, and then split. This is selected, right? I don't want that thing to be selected. So surface things to cut, element to cut is that surface. Cutting edge is this, or cutting element is that, and hallelujah. Okay. Now, because of the way I made this thing, when I mesh it, everything is going to get meshed. And when you put a thickness on it, everything is going to have the same thickness. But I know how to fix that. Let's actually do this. Yeah. Apply material, metal on that, aluminum. Okay. Uh, yeah. So let me go to uh, generative generative structure analysis. Uh, okay, and I'm going to say okay. These sketches are bothering me. You can always hide them. Okay, but since I'm not going to finish the problem, I'm not going to. When you want to put restraints and things like that, you have to get rid of these. But let's mesh it because there's something I want to show you. Okay, and then put a thickness on it. The whole thing is going to get the same thickness. First of all, if you want to fix that thickness, you go to properties, right click local properties, and select the piece that you want to have a different thickness. Maybe this is, I don't know, 1 or something, different from the other guy. Okay? And if you do visualization, okay, the rendering change it because you can't see the elements right there, horrible mesh. And the rest of the problem is the same. It has the correct thickness, top, side, there is no seam there, believe me, there's no seam. But before I'm not going to do the rest of the problem. The rest of the problem is exactly the same. Restraints are the same, pass the load, etc., etc. Now, the only thing you don't have to do, you don't have to put any connections there and fasten connect. You don't have to do that. But I want to show you something else. Let me get rid of this. Mesh. Actually, let me get rid of the whole thing. And delete this obviously, and delete the property too because it may come back. And I don't know, complain that there is no mesh. How do you put a property? I'm not sure. But just delete it. But I want to show you something. Okay, so up to this point, no issues. Instead of meshing it with this guy, you see that with this guy, I'm going to go to the advanced meshing tools. And here's the beam, you can see that. There's this fellow which says surface mesher, or there's a version of it, advanced surface mesher, which you can do a little bit more. I click on this, and I click the surface. Notice that here, it doesn't give you necessarily, it gives you a triangle, but it also gives you the option for four-noded element. You can do that in generative structure analysis. So let's say I say, give me four-noded ones, and let me make this thing smaller, just for the heck of it, 0.2, and say OK. And then I refer to this icon that you see here. I refer to this thing as, it looks like there is a Z there called zap it. Like, you cannot get elements like this in the generative structure analysis. It's only triangle. And these are better. I don't expect you to use it, okay? But these are better than the three-noded. Yes? Okay, how to got to this? Okay. Okay, so let's cancel that. Actually, let me unzap it. There is an unzap here. I think here it says don't do it. Don't do it. Okay, so let's exit. Let me exit. Surface measure right up there. By the way, these are, if you look at the videos of last year, zap it. Select the surface. It says, which do you want, triangular one or do you want four-noded one? I selected this guy. This guy is four-noded. You can see that. It's like a rectangle. Yeah. And then put a size, and you say okay, and zap it. Zap it. Bad choice of words right here. It looks like a Z. Okay, and if you want to keep it, that's fine. The rest of the problem is the same. You can go to generative structure or not. You have to go there because restraints, loads, and all those things have to be done in generative structure analysis. So I go there. The rest of the problem, you still have to go there. And you put thicknesses on it. You have to. So here's the thickness. Operate on the entire thing. Okay? And now you can look at your mesh. It seems that I have two of them. One of them is, I didn't mean it. That was the first one, I think. Let me delete this. Okay. Mesh visualization. There we are. Okay. A lot of problems. Triangular ones are good because they're fast. But these are more expensive, but they're more accurate. Simple as that. Any question? The rest of the problem is exactly the same. Deactivate the mesh, put the restraint, everything's the same. And unless you're asked to do it, don't do it. Just go and do the regular way. Okay, so this takes care of two different ways of doing the problem. The third way that I was going to do for you, but I'm not going to, is you, instead of drawing an L and extruding it so that the things talk to each other, just like yesterday, I can draw a horizontal line, extrude it, vertical line, extrude it, and there's going to be a seam there. You make the hole on top of this, you make the hole on the side of this, the usual way that we did, and then you create a connection between them and make it fasten. Or join them. You can also join them. In other words, when you drew this guy and extruded this guy and extruded and then you made the hole, fine, join them. Then you don't have that problem. Any questions? Okay. So let me get rid of this. And get rid of that. And this is the second problem that I wanted. So we have a pressure vessel, a gas tank. Think about it like that. A hydrogen tank in the back of the truck, something like that. Some dimensions, and we pressurizing it. A very classical problem. You did it in probably formula bodies, the first semester, first course. Now, two formulas that or at least one formula that every mechanical engineer should know, in addition to F equal to ma, In addition to sigma equal to my over A or MC over I, MC over I, that's what I meant. In addition to that, is the thin wall pressure vessel problems. So you have three components of stress here, principal stresses. One is the hoop around, that's the killer one, PR over T. P is the pressure, R is the radius of the nominal radius of the pressure vessel, and T is the thickness. The other one is the axial one. If the ends are capped, this is also going to have an actual stress, but half the hoop. You can see that PR over 2T. And the stress through the thickness. The stress through the thickness of the wall, what is it? It says 0, but wait a minute, why is it 0? It's not 0. You just look at the inside, it's pressurized. How could it be 0? If you were standing against the inside of the pressure vessel, and the pressure vessel was pressurized, don't you feel it, some force on your belly? Because it's pressurized. That's sigma Z. It's not 0. So why do we say for pressure vessels, or thin wall pressure vessels, sigma is 0? Look right there. That's what we read in deformed bodies. How do you justify that? How do you justify that on an interview, the guy would really say, "Do you understand these?" Yes. Can you tell me why is that 0? Because on the inside you have a pressure. Pressure in the thickness direction is the pressure that you apply or stress. So what would you say? Is that a fair question to ask on an interview? Okay. The problem is not 0. That pressure, that stress is not 0. It's actually the pressure on the inside. And what is it on the outside? What is that stress on the outside? Sigma Z on the outside. What is it? There it is 0. Inside it is not 0. So you cannot say that the stress is 0 because on the inside it has a value, on the outside it has a 0. So why are we saying that this is 0 then? It has to do with that R over T. Very big. R over T is very big. Thin wall pressure vessel. T is much smaller than R. So the ratio R over T is 100. So you take the pressure multiplied by 100, that's going to be the hoop stress. Multiplied by 50, that's going to be the actual stress. And the pool pressure in the radial direction, the best it can be is P. The other one is 100, the other one is 50. Actually, the radial one, the biggest one that it can have is 100, whatever the pressure. So that's why we assume it is 0. Okay, so we're going to solve this problem. We can do it based on extracting surfaces or making the surface directly by itself. I'm going to do both. What about symmetry? Use as many planes of symmetry as you can. You have seen a problem like this. What was the problem that you saw that kind of resembled this kind of a geometry? Does anybody remember? Which one? Yes, rotating disk. The rotating disk problem. So, if you were convinced there that any sector that we take can be used and it's going to be, patterned around the disk, same thing is here. You can take any sector that you want, 30 degree, 45 degree, 90 degrees. The advantage of taking 90 degrees is that you don't need a new coordinate system. You don't need a new coordinate system. But if you take anything but 90, for example, then you need a coordinate system to apply those symmetry restraints. And I can guarantee you, on the test, if I wanted people to do that coordinate system, I will tell you, take a 30-degree sector. So don't take 90 then, and you're going to lose more time. Whatever the components of that particular portion is. Okay? So I will take a 30-degree sector. Okay? And by the way, half the height. Let me see now. I don't want to concentrate on these dimensions. So I'm going to make my own dimensions, okay, so that I don't have to worry about this. All right, so let's go ahead to Katia. Those of you who are watching this tape or recording, I'm ignoring dimension. What? What happened? Okay, let's start with solid first. Okay, I'm going to start with solid. So on that face, I will sketch. You know what? On purpose, I'm going to create a whole solid and then make a plane and cut it. Make a plane and cut it. Okay? So let's do that. You can say, can I not make that sector to begin with? Yes, you can. But I'm doing it differently. So, well, obviously here I'm going to go to part design because I want to make a solid object out of that. Okay, so let's say this is half of the height, half the height, half the height. Now, I would like to cut this thing, take a 30-degree sector. Okay? So I have to create a plane that is 30-degree rotated, for example, with respect to one of the vertical planes. Here's how I'm going to do that. Look, if you know, great, I have no problem. Plane, but let's see. What is one of these? It says offset, angle. It looks like this. Angle, something with angle. Okay, so it says what is the rotation axis? I'll say Z axis. What is the reference? So for example, 30 from, I don't know what I picked here, YZ plane. And I'm going to put a 30-degree here. So you can see that it actually created a plane at 30 degrees to that. And I'm going to use that for cutting purposes later on. See this? Okay, now get the split. Get the split. Get the split. Let's first cut it with respect to YZ and keep the other side. Let me flip that. It really doesn't matter. And then I'm going to cut it with that inclined plane. Okay, so another split. Read it carefully with respect to that inclined plane and keep the other side. Flip it. Obviously, that was not what I wanted. That's okay, no problem. Double click on it, flip the direction of the arrow, and say, do this thing any way you want. Okay, I just wanted to show you how you create planes with certain orientation. Okay, so this is it. Let's apply material to that. Material, metal. Okay? And we go to generative shape design to extract the faces. Extract the top face and the side face. Oh, notice that it won't do it. I have to do it separately unless I go to this bag. No problem. Do it again. There. And we don't want this. We hide it. We cannot delete it because these surfaces are coming from that object. We cannot delete them. Yeah.
Those surfaces keep the same material that you apply?
Yes, yes. Because once you put it on the part, anything that's in there, those surfaces are in this part. Okay? Of course, look. Part steel is down here. Everything that's here is in that part. And part is taking the steel properties.
Okay.
Yeah.
How come you would take the bottom surface off?
I assume that already I have. I'm sorry, say that again?
Like, you didn't take the bottom, the top.
Half the height.
Oh, okay.
Half the height. You don't want to lose parts of that.
Oh, so you already cut
Suppose this is half the height of the thing. Okay. Now, because I don't want this issue of connections and things like that, why don't I join them? Join them. Join this to that, so that we don't have that issue of scenes and things like that. Now, because later on I want to apply a certain restraint on these two edges, there is no problem because these two edges happen to sit in the YZ plane. On the other guy, the other two edges are not in the YZ or XZ or XY plane. So I have to create a coding system for that. And let me remind you how we do it. That that thing is right here at the very bottom. There's no way you can miss it. Access system. When you ask for the coordinate system, automatically it creates it at the global origin, which is down there, right there, and oriented with the global coordinate system. I don't want that. So first of all, it makes it easier for me to see things. For the origin, I'm going to select this top one. Okay. This, actually, that one. Yeah. Let me undo this. You know what? I want to put it on that corner, which is not aligned with the edge that I cut. You can see that. But I have a choice of putting any of these coordinates on direction that I want. For example, if I want x along this line, no problem. I say here, x, put the x there. Rotate it so that x is there. You see, x is along that line. The x of this coordinate system. Okay? You say fine. Let's go and do the rest of the problem. I have a question for you. Would you like me to go to the advanced machine tool or generative structure analysis? Okay, no problem because it's so easy. Click on the surface measure. Select the entire thing, and put a reasonable size there. If not, you can change it. Say okay, and zap it. You like that? Okay. Say okay, and then we exit that particular surface measure module. The rest is the same. So we're going to go to the generative structure analysis. Already we meshed it. If you want to see the mesh, right-click mesh visualization. It's right there. Okay, we can see that. Deactivate it. Okay, now we're going to, let's see now, thickness. Thickness on that face, whatever it is, 0.02, 0.2, whatever. Just remember that these formulas that I wrote down for you are valid for thin wall pressure vessel. So if you want to check against those formulas, this better be small thickness. I mean, in principle, you can make it 1,000,000 miles, it'll do it for you. It's garbage, basically. So all I'm saying is that we go ahead and recklessly do this thing. But now, okay, so let's go ahead and apply our restraint. So this user-defined restraint, this edge and that edge lie in the global YZ plane. Global YZ plane. You can see that. Global YZ plane. They do not move in X. Rotations exactly the opposite. Those two other edges lie in this coordinate system conveniently. So let's select the other two edges. I'm going to uncheck these. This edge and that edge lie not in the global, in the user, and I created my user. So the coordinate system that you use is with respect to this coordinate system that you see created. And can you help me with that? What do I fix translation-wise? What do I fix? Z, good. Direction 3 and rotations exactly the opposite. So this and that and okay. Is there something else that I have forgotten to do? The bottom, the bottom edge, the bottom edge, I cut it, I left it alone. So I have to do that. So the bottom edge, and don't clump it. You clump it, you get color. It's completely wrong. This is not clump. It's a symmetry. With respect to, be careful here, with respect to the global one, for example, it is in the XY plane. You could have used the other one, but I changed it to global. I switched it from user to global. It's in the XY plane, does not move in Z. Rotations is exactly the opposite. Okay? Last thing, pressure, load. I don't know what I have, 100 psi. So we're going to apply pressure. Now, I'm pretty sure that you're going to have to select both of them. I'm pretty sure, in spite of the fact you joined it, you have to put it on this. You see this? That's suction, of course. You put a minus there, right? That pushes it in. Okay. Minus. You're going to have to do this thing separately. So on the other one, and that's correct. You can see that's outward. Okay, always pray. These are not too bad, but they're safe. I'm not going to even save it. I'm going to run it. Done. Look at the transformation. That doesn't surprise you. Doesn't surprise you because the piece of this entire structure that's most flexible is on the top and the bottom. Trying to expand the periphery is going to be harder. Okay, but these two bulge out. Okay, if you look at the one Mises stress, you're gonna do some detailed work here. It tells you that in this particular problem, the biggest stress is around the seam up there, and I agree. If it fails, in all likelihood, it's going to be at those wells. But do not take these numbers for granted, because the critical area, one critical area is on the top, I understand, but to get good stress distribution with shell elements on that top is not going to be possible. Okay? It gives you a rough idea, but it's not possible. Generally speaking, when you do this kind of a thing, unless you're designing these guys for the well and things like that, you're interested mostly in the hoop stress and things like that. Okay? So be careful of taking these for granted. Now let me show you something. If I want the stresses here, by the way, look, as I go down here, they're all the same color. If you put the cursor on it, actually, the numbers are also all the same. You see this? Let me zoom in for you. They're all the same, all the same. As you get closer and closer to the top, things will change. But in that area, in that vicinity, everything is blue. Everything is essentially the PR over T and PR over 2T dumped into the formula for one Mises stress. But if you plot the principal stresses, it will actually give you PR over T and PR over 2T. Because principal stresses, one of them is the hoop, the other one is the axial, third one is zero. Third one is zero to it. So if you go and plot the principal stresses, which was totally useless for beams, here you can actually get things that you did with Dr. Green and whoever taught you in the first course. Principal stresses, and in fact, these values are PR over T and PR over 2T. In fact, if you zoomed in closely, you see one of them is double the other one. Yeah, see that? The hoop stress is double the other one. You multiply 5 by 2, you get 10. Okay. Now, one other thing I want to show you. You might say, you know what, this is fine. Let me actually put this thing back where it was. Average ISO right there. Nothing exciting. Now, which stress is this? Principal stress. But if you want to know which one you're plotting right now, let me go there. Under more, you can say which one you want, C11 or C22. If I change this thing, it's going to be half the value. But my point is something else. Sometimes you get the von Mises stress, for example, or any of these, and you want to stay away from that top because you know that that top could be garbage. You want to stay away from that. Only you want to show the stuff, for example, here. So what you do is you go and create, let me deactivate this block first of all. No, okay, we can leave it. You go and create group. Katia calls it group, and there's different ways of making it. For example, I can make I don't know, a box group. It says, okay, where do you want this box to be placed? Well, I don't want it to be placed there. So I'm going to move it. I can move this. Let me see, does it cover that? If not, I resize it so that it actually covers it. Sure, yeah, okay. There. Just show me the stuff in that box. No problem. Let me hide the box first of all for you. You go to the place where you decide on what you want. You say, just show me the box group. Don't show me any other garbage. Don't show me any other garbage. Just show me this. Wait a minute, what's all these colors? Why are the colors different? Are they not supposed to be the same? Yes? Strings? No, strings are there. This is just looking at this particular piece. Just looking at that zone. Yes? What is the range? What are the numbers? They're all the same. But for plotting purposes, it has to do something. Just be careful. Colors don't mean ignore the numbers. Those numbers are all the same. Okay, listen, I am not going to do this thing the third way. Let me just show you. Let me just show you. I'm not going to finish the problem, but I want to show you how to create this geometry in 20 seconds. Let's start with the part. Okay, 20 seconds. It's not going to take more than 20 seconds. I can guarantee you that. On that plane, I will sketch an L. Exit and revolve it. Katia does not call this thing shaft. In generative shape design, it calls it revolve. See, these are different ways of making surfaces. See that? These are different ways of making surfaces. We have already done extrude, and there's one here which says revolve. So it says revolve this about the z-axis. By how many degrees do you want? Let's say 30 degrees. You don't have to join these. Just like when I extruded, I got a single surface. You just revolve it. The rest of the problem is exactly the same. So let me stop this recording first of all, and then I talk about